Oggi pomeriggio c'è Michele Casini, welcome Michele. Your presentation is a specialist in Balkan in the North Sea. 20 years ago, about in the 11.
I have been there 22 years. Yeah.
Okay. Prego, Michele.
Okay, I start.
Sì, sì, sì.
Okay.
I speak
Okay. Thank you. So, good morning or good afternoon. So, are you all here? Yes? Somebody is coming? Okay. So, we speak in English, right? Okay. And the link is on now. So,
link is on. Okay.
Okay. So, from home, can you see us, me, or?
Okay. Teams, okay?
Teams, okay?
Okay.
So we can start.
Start.
Okay. So, first of all, I want to ask from where you come. So, some from Italy, I know somebody, and then the others. Yeah, Italy. And then the others. China. Right? You too? No. Okay. Russia, yes. Something more.
Spanish.
Okay.
Brazil.
Okay, so my name is Michele Casini, and actually I work here in this building at the University of Bologna. And I have been for 22 years after my graduation at Bologna University. I moved to Sweden, and I did PhD there, research, done on my career in Sweden. Then 3 years ago, I came back to Bologna. Now I'm teaching the same language where I was like 4 years, not 4 years long, but 30 years. So actually, what I wanted to present today is something about not Italy, not the Adriatic Sea, not the Mediterranean Sea, but about the North Sea and the Baltic Sea. About the North Atlantic. So I want to ask also who is familiar with the fisheries hub. I know. Something more, yes. And the others, what are you doing? Actually, what are you doing? Journalists. Okay. Research biologist, economist. Sorry. Which way? Okay. Somebody working with mineralization for sure. Thank you. Something more? No. Just to know what you are doing. So we talk about the North Atlantic, maybe the Baltic Sea, because I've been working for very long in this area. So it's the only thing I know. I don't know so much about the Mediterranean. Okay. This is not the first step.
Yes, okay.
Is it not? Okay, yes. So this is the title. So we talk about the trophic interactions. If somebody doesn't understand what is written, what I'm saying, just ask, okay? So that everybody's on the same page. So we talk about trophic interactions, the interaction between species. We talk about climate change a bit, and we talk about management of resources with focus on the Baltic Sea. Okay, this is more or less the outline. So I will first start with the introduction about ecosystem functioning in general. If you did some courses in ecology in your studies, you were for sure you have been talking about ecosystem functioning. Then we go into the Baltic Sea, and we look at the main population in the Baltic Sea, the main commercially important population. We talk about the physical properties of this sea. Then we start to look more in details about the Baltic cod. The Baltic cod is a species, we will see later on, that being probably the most important commercial fish species in the world, let's say, in the last, I don't know, 40, 50, 60 years. Then we talk about a project that trying to improve the management of this population in the Baltic. Then we talk a bit about ecosystem-based management. We see what it means. And then we talk about management. Okay, what kind of management options we have to try to manage in the best way this population, that is the Baltic cod. Okay, so I tried to divide this seminar in 3 or 4 different pieces, so see if we can make it 40, 45 minutes for each. Usually I don't speak so much, so I don't think I make it to speak 4 hours. So with maybe 3, okay. But if we want, also some of you can come here to write something. So everybody's keeping awake in the afternoon. Okay, we try. Okay, first some general things about ecology. This is something that we do in the ecology courses, basically. You know the difference between bottom-up and top-down mechanism in the community, in the ecosystem. Everybody knows this. Okay, somebody who studies ecology, for example, Federico. Do you know the difference between bottom-up and top-down?
So from an imperator, for example, or if something is controlled from the bottom, such as phytoplankton or something like that.
Yes.
And then the whole ecosystem is regulated by this tool.
Okay. So it means that if something changes at the top of the food chain, like let's say one top predator, I don't know, tuna or killer whale, sharks, like that, it will affect the whole food chain. Because if a big predator, for example, is disappearing, the prey of this predator will increase, the prey of the prey will decrease, and so on, until reaching the bottom of the food chain. Instead, bottom up is the opposite, right? It's something starting from the start, from the bottom of the ecosystem, moving up to the top predator. So it means, for example, if temperature increase or salinity increase, can increase also primary production, phytoplankton biomass. And if phytoplankton biomass is increasing, the all levels of the trophic of the food chain would impair increase. Okay. So top down and bottom up. I will talk quite a lot about this. So this is another way to see it. This is a very famous paper from Curie and Shannon from 2004. And this is an example bottom up. So something changing from state 1 to state 2. That is propagating up to the food chain. Instead top down, in the middle, something starting from the top, propagating down the food web. And then there is this third wave of waste. That means that something is happening in the middle of the chain, propagating up through bottom-up effect and down through top-down effects. Okay, this is just. I was teaching ecology this morning, that's why I use the same slides actually. Okay. So the focus area is the Baltic Sea. Somebody's not familiar with this, I guess. So the Baltic Sea is this, the North Atlantic. The Baltic Sea is this area marked in red. And as you see, I mean, it's called Baltic Sea, but it's not really a sea, it's like lake, more or less. So it means the salinity is very low. We will see later what it means. So if you can see here, basically, let's see if I can move something. So it's a lake and it's connected to the North Sea, so to the ocean. only through this, they're called Danish Straits, because there are these straits that are between Sweden and Denmark, so they're called the Danish Straits. So the connection with the open sea is very limited. That's why salinity is very low. Okay, so the Baltic Sea has very low biodiversity, especially in the open sea. Very low biodiversity because the salinity is very low. So there are not so many marine species adapted to the sea. Very few, fewer than the Mediterranean Sea, for example. So the biodiversity is very low. That means that the trophic interactions are very strong between each other. Okay? And many species are at the limit of their distribution. If we think about marine species like the cod that we see later on, herring, sprat, other species, they are at the limit of their distribution because salinity is very low. And you can see here the salinity in this picture. You see here you get to 30, like Mediterranean Sea, 33, 34, then 20, and then in the northern Baltic Sea, 3 PSU. So it's basically freshwater, is a lake. And another peculiarity of this sea is that the size of almost all the organisms is much smaller than in other areas. That is probably also due to salinity. So all the fish are not getting big sizes. Okay, in the sea we have multiple pressure acting, as in the Mediterranean Sea also. So we have very intense fisheries. We have, of course, hydrological changes, climate changes. We have a big problem of eutrophication, so emission of nutrients from agriculture, basically, increasing the productivity of the sea and creating this summer and spring phytoplankton bloom, for example. And we have pollution. The problem of pollution has been decreased in the last 20 years, but it's still there. So the main pressures are actually fisheries, climate change, and eutrophication. So one of the main problems is oxygen in the Baltic. So you see here a big picture of or drawing of the Baltic Sea, and you see these black dotted lines, and is a section that actually showing the bathymetry of the Baltic. And this area that is black and the red is representing oxygen. So you see the red areas, they have oxygen around 2 milliliter per liter. So very low oxygen concentration. So you see the very big water masses have very low oxygen concentration. Also because there are very deep areas here, almost without oxygen. And actually this problem of anoxic areas increased a lot in the last 25 years. So one of the big problems, also due to climate change, has been increasing of what we call hypoxic areas. So hypoxic area means areas with low oxygen content. And instead, when we speak about anoxia, so anoxic areas, we are meaning that the water actually don't have oxygen at all. This you see the time series of the anoxic area up to the top in square kilometers. So you see that until the mid of 90s, the areas without oxygen were quite low. They started to increase. And in the last 20 years, we have observed very big areas without oxygen. Here is a comparison between one period with no anoxia, more or less, and a period with hypoxic condition. So the gray areas are areas with water below 2 milliliter per liter of oxygen, and the black areas areas with oxygen below 0 milliliter per liter. So it has increased a lot. Of course, one of the main problems is increase in nutrients coming from land. You see here that the catchment area of the Baltic Sea is very big, and not only is very big, but is including many different countries. Here we go from Sweden, a bit of Norway also, Finland, Russia, Estonia, Latvia, Lithuania, Poland, a bit of Germany, Denmark. So there are many different countries. Of course, nutrients actually is going into the Baltic Sea. We have a very complex political, of course, situation. 9 countries surrounding the Baltic Sea. 1 is not EU, Russia. So this makes all the decision making very, very difficult. And not only within the European countries, but also between European countries and Russia, of course. Okay, so now we will focus on the main area of the Baltic Sea, what is called the Central Baltic Sea, sometimes called the Baltic proper, Central Baltic Sea, and so on, but we focus on that area. And the numbers that you see here correspond to what is called subdivision, that are different management areas, we can call it, just to simplify. And here on the right side, you see the very simplified food web of these central areas. So we have the fishery, of course, at the top of the food chain, fishermen. Then we have the cod. The cod is the main predator of the Baltic. So today we talk mainly about cod. We'll see why later. So it's the main predator. In this area, you can find also, for example, salmon, that is also a top predator. You can find seals. Actually, seals is the top predator, but we talk about fish today. So the top fishivore is cod. Then we have 2 pelagic fish species, herring and sprat. Sprat is also here in the Adriatic Sea. You find that in the northern area, you find a lot of sprat, not herring. Herring is not present here in the Mediterranean Sea. Then we have the plankton, some other animals that we don't care about right now. Then we have phytoplankton, and of course nutrients. Okay, so we try today to focus on cod, sprat, herring, and a bit about the plankton to see what is going on in the ecosystem. So far, you understand all the terminology, all things, okay. And we focus, yes, on these 3 fish species. There are others, but today we speak about those. Okay, these are the changes in time of these 3 species. So on the x-axis, you see time. On the y-axis, on the left side, you see sprat and herring SSB. SSB means spawning stock biomass. So it means the biomass, so the total weight of the fish that are spawning, okay, giving, contributing to spawning, to reproduction. Okay. And on the y-axis, on the other side, you see the cod spawning stock biomass. So the total weight of the fish that are reproducing. So here you see the time series of cod, the red one. You see that it was quite low in the beginning, then had a big peak, then went down. And then here you see then the last 4 or 5 years, you don't see any data. I will explain why later. So cod went down and then crashed. Okay. Sprat more or less showed the opposite trend. First it was quite high, then went down, then up again, and then stayed at quite high level. And then herring is the blue one. Okay. We think the sprat and cod showed opposite trends, mainly because the sprat is the main prey for cod. So we think that when cod disappears or goes down in abundance, his main prey, the sprat, start to go up, which is an example of what kind of mechanism. Bottom up, top down. What is that? Bottom up. Yes. Okay. In the Baltic, there are 2 cod stocks. For management purposes, all these the species is divided in different population. that we call sometimes stocks. Here in the talk, I use stock of population as synonymous. It's not totally correct, but you see, when I speak about stock, I mean a population. Okay. And the Baltic Sea, there are two stocks. So the population, one that is called the Western Baltic cod, that is colored in yellow, and then the Eastern Baltic cod. So everything else, everything that is in gray. So if we look at the species, you see the distribution here. Now we focus on two stocks on the two stocks of the Baltic Sea. And now we see what happened to this cod population during the last 20, 30 years. So first of all, we have seen that first increased in abundance or in biomass and then went down. And we have seen also a contraction of the population. So if we go back in time when the cod presented this peak, the cod was distributed more or less everywhere in the Baltic Sea, also in the northern part where salinity is very low. So we could find cod up there and very big cod. But after the decline, actually we are seeing the cod has contracted in the southwest. So now the cod is mainly concentrated in this area. And why do you think it has concentrated in that area after the collapse? Why squeezed in this area from what we have seen so far? Some ideas?
Nico, allora domani io non vengo.
Could be. We come to the prey later. We see that it's the opposite actually. So the prey moved north, but you didn't know yet. But why the cod when the population goes down, so the density goes down, not the density, the biomass goes down, started to be contracted here. Can you repeat? There. Okay. Which environmental condition can you think about? So salinity, why? Yes. So salinity here is much higher than up north. Okay. So for a marine species, it's better to have salinity that is higher, right? Oxygen also, somebody said that. Yes. I mean, this basin is not very deep, so the oxygen level is a bit higher than more north. It can be another reason. But anyway, of course, when the total biomass decline, the stock tend to be concentrated where the environmental conditions are better, of course, right? So we have this contraction to the south, southwest. Another change has been a decline in site maturity, so the sites at which they become mature. So if we go back in time, in the 90s, they started to be mature at around 35, 40 centimeters. Now they start to be mature at 20 centimeters. So already fish that is 20 centimeters start to reproduce, which is quite strange. Cod can reach, I don't know, in the Baltic Sea, 1 meter or less. And we see how this size also changed. So the size, what we call size of maturity decline. We have seen an increase in parasite infestation, infection infestation. That you see the picture of the liver of cod, very disgusting actually. And these liver parasites are nematodes coming from seals. So the seal is the final host of these parasites. And we have observed an increase of this infestation in the livers in the last 20 years. So nowadays, when you go out to sample, you see, I don't know, 60, 70% of these fish full of parasites in the liver. Another trend has been a declining condition factor or condition, so the fatness of the fish. The condition factor is like if you think the weight of the fish divided by length, so how big is the fish, how fat is the fish. You see this black line going down. And this is the difference between what we could find like 20, 25 years ago and what you can find now if you go out fishing. So now this small and the thin cod are called the ghost cod. because it's just bones. There is no flesh, no meat, just bones. And there's been a big change. These instead bars are the percent of fish found below a certain condition threshold of 0.65, I think. And you see that this proportion has gone from 0 basically to 40%. So when we go out fishing, take samples, we find more or less 40–50% of cod below this threshold of 0.65 condition, which means that these fish are supposed to die soon because they don't have energy basically. So it's been a worsening of cod condition time. Not going very well for the cod, no say. This is something. Okay. This is the last figure showing the change in time of the mean size instead of cod. So on the y-axis, x-axis, you have total length of the fish. On the y, something happened there. Is abundance. Okay, abundance. So the length frequency distribution of the population. So if we go back in time since the 90s, you see that we could find in the sea, some recruitments or some small fish, but also many big fish, up to, you see, 80 centimeter, almost 1 meter, even more. But in the last 10 years, especially in the last 5 years, actually the whole population size has contracted. So you see the red curve there. So when we go out sampling now, all the fish are more or less between 25 to 30 centimeters. So the population size has, mean size has increased. So this is a picture, very famous picture in the Baltic Sea. This is my colleague, now he's in pension. This is a photo from the 80s. This is a Finnish colleague, Eero, it's called. And this is a photo from the northern Baltic Sea in the 80s. So that you can see the huge Baltic cod that were found in the sea back in time. Okay. Now, as I said, they are solo. So it's a big change. So we are seeing declining condition, so they are thinner, shorter, they reproduce earlier, or at a lower size, increased parasite infection. They contracted the distribution to the south. That's enough. So for the cod population, it's not very promising like time also for the future. What is it? Okay, so of course we have observed this fact that these individuals have been shorter and leaner, so thinner. So of course these have huge consequences on the fishery, of course, because the fisherman wants big fish and fat. And the fact that the size has gone down and also the condition has gone down means that these have very big problem with the fishery. So these red bars show the percent of fish above 38 centimeters that some years ago was the minimum landing size. So if the fishermen caught a fish below 38 centimeters, they were not allowed to sell, for example. So they needed to throw back to the sea. Now it's not allowed anymore, but just here just to show that the percent of fish that are big below above 38 centimeters went down. This is still in Italian, sorry. I will translate this. So the catch for all the fish that the fishermen were catching were difficult to sell. Basically because they were thin and short. So they were difficult to sell. This provoked also an increase in the discards. So it means that if the fisher didn't like the fish that they were catching, they were discarded in the sea. Sometimes it's called also high grading. So it means that substituting one fish that is better for one that is not so good. And the fishermen basically also had problem to fill their quotas. So in this area, the fleet, the fishing fleet, as a quota, total quota. So, for example, the cod, the Baltic Sea, had a quota, I don't know, 50,000 tons. It means that in 1 year, the fishermen could fish only 50,000 tons. Basically, since the size went down, the condition went down, they were not able to feed this water. So they were not able to deliver fish to the industry, basically. And this had a big problem, of course, for the whole industry. And this is the same year. So in the red lines shows the biomass of the fish above 35 centimeter. Instead, the black line, the time series of the total reproductive fish. This again just to show that the mean size has gone down. Okay. Okay. There is something unclear so far. So for the cod, everything went bad in the last 20 years. And sometimes also we are thinking about if we should continue to investigate this Baltic cod, because personally I don't see any future for the Baltic cod in the Baltic Sea, because with climate change, temperature will continue to go up, salinity probably will continue to go down, anoxic areas will continue to increase, so there is no space for a marine species like cod in this area. That is my personal opinion. Okay, we have seen the fisheries effect of this decline in growth and condition, means that the fishermen were not able to fill their quotas, and the revenues from the fishermen were also lower because the quality was low. Now we look a bit at the ecosystem perspective. So what does it mean that the cod population went down and all the fish now are very short? You understand this figure? So on the x-axis you have the cod length in centimeters, and on the y-axis you have the frequency distribution of the prey that they eat. So you can see that the more, when the cod start to be bigger in size, they start to eat more herring and sprat, so pelagic fish, and less benthic animals. And so they eat more in the pelagic water. So in your opinion, if the population of cod declines and the size also becomes smaller and smaller, what consequences can have on the pelagic fish, for example? Increase. Okay. So increase not only because the predators are not so abundant, but also because the predators now are very short. So they eat more benthos and not so much pelagic fish. So the pelagic fish should increase in abundance. That's what we expect. So predation pressure on forage fish is pelagic fish, herring and sprat is reduced when the cod is small. So this is an old paper actually, but I still present many times. So here you see what is called the top-down effect through many different trophic levels. So what we call a trophic cascade. So in the top graph, maybe it's easier if I do like this. So when the cod decline in abundance, but also in size, we are seeing his main prey, that is the sprat, increase. And you will see here the decline in cod, the increase in sprat. And when with the increase in sprat, we observe the decline in zooplankton, so which is the food for the sprat. And at the same time that we observe the decline in zooplankton, we observe also an increase in phytoplankton, which is the food for zooplankton. That's what is called trophic cascade. So something starting from the top of the food chain, cascading down all the trophic levels. So from this, it seems that the disappearance of cod and then decline in size has caused all this kind of chain, if you look in statistical way, at least. So back in times, in the 90s, we had a lot of cod, not so many sprat, a lot of zooplankton, and not so much phytoplankton. From the beginning of the 90s, we observed the opposite. So the cod population declined a lot. The sprat population increased, the plankton abundance declined, and phytoplankton blooms increase. So this means that the big phytoplankton blooms that we observe sometimes in the Baltic in spring and summer are not only due to eutrophication symptoms. So it's not only due to nutrients input in the sea, but also to this cascading effect due to the elimination of the top predator of the system, what is called top-down regulation trophic cascade. One particular thing that should keep in mind, we'll come back to this later on. Remember that I said that when sprat increase, the plankton goes down, right? At least if you look at the time series of the data that we have. This figure shows that the relation between sprat abundance and the plankton. You see that this negative relation is there only when the sprat population exceeds a certain threshold. You see this in this graph. So until a sprat abundance up to 15, 16 millions, trillions, whatever it is, this number, individuals. Below that, there is no effect of sprat abundance on the plankton. But after that, so when the sprat abundance is above this limit, you see this negative, at least correlation. We are not sure that this is a cause-effect thing, but at least there is a strong correlation. So it means that the predation effect of sprat on the plant seems to be there existing only when the sprat abundance is above a certain threshold that we estimate around 17, whatever it is. And we come back to this because when we speak about management, we will come back to this figure. Okay, the last step of the trophic cascade is phytoplankton bloom. So we have seen that in summer, at least in spring and summer in the Baltic Sea, we have seen an increase in these phytoplankton blooms. And phytoplankton blooms are made up not only of dinoflagellates, diatoms, others, but also cyanobacteria actually. And so this has been a workshop that was held in European Parliament 10 years ago now, or 12 years ago, where actually the European Parliament was interested to know if fishing had an effect all the way down to the food web until the phytoplankton biomass. So we were there discussing in this workshop about that. And actually this fact that we observed this trophic cascade, so from main predators to phytoplankton, is something that is not observed only in the Baltic Sea. It has been observed in the Black Sea, in outside Canada, many different places, especially in those systems with low biodiversity. We come back to that. So this is just to say that when in the Baltic Sea at least, the increase in phytoplankton bloom in summer during the last 20 years has been linked, at least in a statistical way, with the disappearance of cod from the system. Okay. This is another very nice paper, I think, from Frank. Frank is a Canadian scientist. Also, this is quite old, 2007. But what he did was that he analyzed in what kind of systems we could observe the bottom-up or top-down effect. Yeah. So he took many different data from different ecosystems in the North Atlantic, close to Europe, close to Canada, USA. And he tried to see if his data told him that it was mainly bottom-up or top-down effect. And the results of this show that actually you could find bottom-up effect in high diversity system and top-down effect in low biodiversity system. And so if we put the Baltic Sea in this map, because in this study, the Baltic Sea was not included. So if we put the Baltic Sea in the map, we say more or less that the number of species here around roughly 60. We observe mainly top-down effects, so negative interaction between trophic levels. So it seems the Baltic Sea to fit to this correlation that they found. But the question is, why do you think that in low biodiversity, so low diversity systems, we observe more top-down effects? Why is that? And why? Could be. Yes. Everybody understood what your colleague said? So in the system with where the biodiversity is high, if one species declines or disappears, there are other species taking the functional role of these disappearing species, right? But in low biodiversity system, if one disappears, the species disappears, there is no one. There is not another species substituting the first species. For example, in the Baltic Sea, you have the cod. But if the cod disappears, there is no other predator in the system. There is salmon, okay, but salmon is another kind of fish. So it's not substituted by another species. If the cod is gone, the predation effect on the pelagic fish is gone. Okay, that's why it's easy to find this top-down effect in seas like Baltic Sea or in low biodiversity systems. Okay, I think we make a break. Do you have something that you want to discuss on what we have? We look. Yes, oxygen. Maybe. Yeah, let's see if we can go back quickly. This I can try to explain at least. So, as you know, the Baltic Sea is connected to the North Sea by this Danish Strait. And so fresh water, salty water, and oxygenated water are coming from the North Sea via the straits. And in the past, so if you go back in the 30s, 40s, 50s, 70s, these what we call inflows, very big inflow of water from the North Sea to the Baltic Sea, were quite frequent. In the last 20, 30 years, these inflows didn't happen. So we didn't have these big masses of fresh water or salty and oxygenated water from the North Sea coming in from the Baltic Sea. And this seems to be connected to the change in the air circulation. The water masses and air circulation. So this inflow coming in didn't occur in the last 30 years. Maybe one or two in 30 years. Back in time, we could observe one big inflow every 6, 7 years. Like El Niño, so something that happens frequently. But in the last 30 years, this inflow stopped, more or less. And this is because of the change in the global circulation of the water masses and that. So that is one first point. The second point can be due to increasing temperature, of course. Increases the stratification of the sea, of course. And another additional point is nutrient emission coming in. And in the Baltic Sea, everything that is going inside stays for 40 years. So the residence time is very long. So if you put something in the Baltic Sea, it stays very long. And then it gets into the sediment also. So he has a big inertia, the whole ecosystem. But basically, mainly due to this fact that the inflows basically stopped. Nowadays is the situation it is. So this is an example for 2013, but basically didn't change after that. So there are very big areas without oxygen. So of course everything is dead there. So you can find only some bacteria maybe, but everything else is dead. Nothing can live there. Okay. So we go back here. Okay, we talked about top down. Something else? No? Okay. So now I would like to present a project that we did in the last 4 or 5 years. And basically what I'm presenting is the work done by one of my old PhD students, Monica Mion, that Luke knows well, or maybe some other of you. And so many of these results are coming from a PhD in Trophic. So if we go back to this slide, so this slide is telling almost everything. So, right, so the size distribution of the coders contacted. And so I guess one of the main questions is, the question is, why? Why do you think, I mean, there's been a contraction of the size distribution of the species? We're talking about size now, so we don't know the size. Maybe here. Why? So the big coders disappeared. They're not there anymore. So I told you before, if we go out with our survey, take some samples, they're all around 25, 30 centimeters now. And back in time, I've seen this picture with this Finnish guy hugging big cod. This is gone. So the main question, also from the management point of view, is why this happens. So I ask you, why? Okay, can you develop?
They need to take what the customer requests to be caught.
Okay.
So they start to fish the large cod, and maybe medium size or little cod have been discarded, or maybe they are overs, and they basically they've been, I would say, suffer a bottleneck selectivity, and so they in order to face the.
Okay. So you are saying that okay, the first mechanism is just extraction of the big ones from the sea, so mechanical extraction from the fish. Okay, for sure. Yes. Something more?
I think that there is both the definition of this factor, but also probably the changing in environmental condition that decreasing the low performance of both.
Okay. So you're speaking about growth.
Yeah, grow rates.
You are not speaking about growth. You're just speaking about extraction of the big ones, or the medium one before they have had the chance to grow. Okay.
Yes, it was the more
Yeah.
because the vaccine is from less supportive to the population in an environmental way. They also can affect the growth of maybe the large pods were already kind of depleted and they cannot become so big, and also they were mechanically removed from the valley. So
Maybe the fish selected
as it's a combination of
evolutionary the slow growing one.
Yeah.
Okay. Okay. Yeah. Okay. Growth over. Something more? Yeah.
The time shift is quite short to observe.
Yeah.
Yeah. Even if, for example, my PhD, I'm studying species of the same family. This hypothesis was, yeah, probably fishing activity is selecting this, but we found that
Was not that.
the decreasing in size was only due to the change in the growth rate.
In the growth rates. Okay. So you have examples in the Mediterranean Sea, Adriatic Sea. For example, what species?
And my PhD species whiting,
White.
Berlandus berlandus.
Yes.
We observed the same pattern.
Another species like ache or something else?
I can think but please help me. That probably there is quite a lot of problem with the age assessment. Right?
that is
And then it's quite difficult to have a precise assessment, but also to say how it's changing from the baseline.
But the size changed.
Yeah, the size.
The mean size, for example.
Yeah, for sure.
Yes.
Yes.
Of thinking that it's something just related to fishes. So I think that on the
Even it's probably more difficult to start because we have different population and also that the potential dispersal of larvae is more effective in whiting from the there is a very population, then it's quite easier to define.
Okay.
there is also something related to that references.
Yes.
That's the question.
Yes. Also here, the young stages are in more shallow area, and the big ones deeper, if they can go deeper. Without oxygen, they don't go. So without oxygen, what do they do? Or stay close to the coastal areas, or they become pelagic. And for a cod, I mean, cod doesn't want to be pelagic, wants to be on the seafloor. But here in the Baltic, they are forced to, many of them, to become pelagic to avoid anoxia.
But on the other hand, it would be easy fish if they start becoming pelagic.
Easier.
Easier, yeah.
I don't know. No, I don't think it's easier to catch pelagic fish than a fish that is on the seafloor. But anyway, very good. So why? Is so high selective fishing pressure can be one reason, of course. There is also other predators. So we have talked before about seals, for example. There can be high natural mortality on the big ones or on the medium-sized one before they have the chance to grow. Growth rates, and of course, if it's a problem of growth rate, we would like to know when during the lifetime they have this bottleneck, and why also, why they decline in growth, if we see that is a growth rate. And then the question that we want to answer is if we can do something about it. So from a management point of view, if we can do something that can help cod to grow quicker if it's a problem of growth rate. Okay, so we go back here. So the question that we had was, is this contraction in size due to low growth or high mortality of the big ones? Okay, so for you who work with in fishery science, maybe this is totally clear, but maybe not for others. So to answer this question, if it's a problem of mortality or of growth, what can we do? In what way can we answer to this question? I don't ask you, I ask the people not working with fisheries or fish growth. So how can we do to answer the question if the growth has changed in time? So how quick the fish is getting big during his life? What is the most? So now we want to know if the growth rate has changed or not. So the question is due to mortality, this increase of less distribution, or to growth rates that has declined. So the fish don't grow. How can we answer that question? Usually in fish, what we use the otoliths to age the fish, right? So if we can age the fish, and we have otoliths back in time, we can estimate the age, we can estimate the length, and see if this curve has changed or not. right? So this curve. So age on the x-axis and mean length on the y-axis. This is a function called the Bombe-Atlantic growth function, doesn't matter. So the fish growing, no, right, in time. So increasing age increases also the length. And so how can we know if this growth has changed or not? If we have the otoliths, we have the length of the fish, we see just if this curve has changed in time or not, right? Because the problem could be that all the big ones have disappeared. Not the big ones, the old ones have disappeared. Okay, so maybe this is due to fishing mortality or natural mortality taking away the big fish. So actually the first stage classes grow as before, but we don't find the older ones because they've been eaten. Okay, so this could be the first outcome. The second one, instead, the lower curve, is that we still find the old ages, but they don't grow. So they grow less. So the growth rate has changed. Of course, and then there are other. We want to know when actually this change has occurred. Okay, this is some animation, but okay. How can we do to answer the question? So I said before, if we know the age of the fish and we know the length of the fish, we can see if this curve has changed in time or not. The problem with the Baltic cod is that for the last 10, 15 years, we were not able to age the fish using the otoliths. Everybody knows what is the otoliths. Everybody? Yes, okay. So usually in fishery science, you use the otoliths to age usually the fish. Okay. For the Baltic cod, we did the same for many, many years. But in the last 10 years, 15 years, we were not able anymore to estimate the age of fish because all these prints from the otoliths that we used to estimate the age disappeared from the otoliths. They are not there anymore. There is something, but you don't know if they are annual rings, if they are marks, if they are something else. So we were not able anymore to age the cod. So it means that we are not able to answer the question if it was matter of growth or mortality. Understand why? So the question still remains: has growth decreased or fish just died? And we were not able to answer that question. Okay, this created a lot of problems in the Baltic Sea. So it means that the growth of this fish was unknown, the mortality was unknown. There's not been any evaluation of the stock status, analytical assessment for 4 or 5 years between 2012 and 2018. The scientific advice that we gave to the European Commission were very uncertain because we were not based on stock assessment data. The management became very problematic. And this quality label, Scacella before talked a lot about this, was suspended by the fishery. So they were taking away this quality label from the fields. So it created a huge problem in all the stock assessment and management chain. This is an article saying Eastern Baltic fisheries lose MSC approval. So this has been already covered this argument this morning, so we don't go in deep into this. So it means that by not knowing growth, by not knowing mortality, we were not able to evaluate the status of the stock anymore. So this advice that we provide every year to the European Commission was very uncertain. We didn't know what. We were not sure about the state of the stock. So this created a lot of management problems. And finally, this quality level was suspended from the cod fisheries fleet. So we wanted to try to solve this problem. So to answer the question if the decline in size was due to growth problem or to mortality. So what we did was to start a tagging project, a tagging experiment. So if you want to have some news about the news or some information, you can go in this website. It was an experiment between done with the collaboration of 4 different countries. It was Sweden, Denmark, Poland, and Germany, covering the whole Southern Baltic Sea because, as you remember from before, the stock has contracted in the third, in the last 20-25 years. So we started this project in 2016, and the idea was to tag fish. So to put a tag, so to fish, put a tag on some individuals, put them back in the water, and hope catch them back sometime after some months, after some years. And of course, from the difference in length, from when we caught and released them, and when we caught back them, we could estimate the growth in length, right? And we were lucky because this could be compared to tagging experiments done in the past. Just because in the Baltic Sea, they did tagging experiments in the 40s, 50s, 60s, 70s, 80s. So we were able to compare our results with results back in time. So we started this project. And this, some of you are familiar with this. So we used this spaghetti tag, they are called. They are this, you can see here, placed on the, close to the dorsal fin of the fish. They're like an anchor attached to the flesh of the fish. And in this part, you have information about the fish itself. So we have an ID number for each fish. So the experiment was done like this, that we were going out, we were fishing some individuals with straws, with gill nets, with different gears. We took them on board, we applied these tags. Each tag had a unique number. Okay. We measured the length, the weight, just the length and the weight of the fish. And then, after applying this tag, we release the fish back in the water. Okay. The same with the cage, with the same depth where we caught them. So following a procedure that is very much used to all over the world, this kind of procedure. And this tag had like a telephone number here, all information related to this project. And we tagged, if I'm not mistaken, 30,000 individuals, more or less, in 2 or 3 years in this area. So we were hoping that after release, that the fishermen would catch them back, probably after months, years, and so on. So these are the photos about caught tagged. This is caught. Yes.
We already had some catch from this.
Yeah, we have the results. I showed you the results now. Yeah, explain a bit the story. Okay. But then, of course, this project needed to be advertised to the fishermen because we were hoping to get these fish back from the fishermen. Okay. For example, we were hoping also to get back from our own survey, but in 7 or 8 years of service, we never caught any tag caught with our own survey. So we were relying on the fishers for this. So what we did, we planned, this advertising paper that we were selling to the fishermen, for example, for Christmas, for Easter, for other gifts. So just to tell them, look, there are a lot of cods in the sea with a tag. If you catch one of those, just call us. Okay, we take the fish because what do we want to do with this fish? We want to measure the final length to know how much they have grown in that period that they have been in the sea. So this here is in Swedish, so difficult to understand. But on these postcards was written all of the information about what they should have done in the case they would have caught one tagged fish. So it's written there, okay, take care of the fish. If you want, take length, weight, everything, but put in the freezer, put in the fridge. Call us, because on this tag, on this spaghetti tag, there's a telephone number. So call us, we come, take the fish, and we do all the runs. So we want to know length, weight, but then we wanted to take the otoliths. We wanted to have the sex, the maturity, all the biological information that can help to understand what is going on. So we were selling these postcards. We disturbed them many times, also for Christmas, like present. We are delivering all this postcard to all the fishermen fishing in this area in 4 nations. Okay, for everyone. Okay. How many do you think we got back? So we tagged 25,000, we can say. How many we got back? So we tagged 25,000. Okay. 350 more or less. Very little. So we were hoping for more, of course, because to make statistics, we wanted to have 1,000 fish or even more. We got back 300, 350, I think now. And the problem, why we got so little fish back? One, because not all the fishermen were willing to help. Okay, but we don't think that has been the main problem. The main problem has been that now the fishing boats are equipped by this automatic cleaning machine of the fish. So it means that the fishermen are not looking each single fish coming up. But there is a big machine just cleaning the fish. So many of these tagged fish probably have been just lost in this cleaning procedure. So anyway, we got 350 fish back, and we tried to do some analysis of these 300 fish back. Okay, first of all, we compared with the fish back in time. So back in time, we had, we had 5,000, I think, a recapture from all tagging experiment done in the 50s, 60s, 70s. So this is the way actually the data are analyzed. On the x-axis, you have the age. On the y, you have total length. And each of these black lines is a fish. Initial length and final length. So for example, if we take this black line, so this is indicated initial length, maybe 90 centimeter. This is a final length, maybe 100 centimeter. So this fish doing its life in the sea has been growing, I don't know, 10 centimeter. Okay, so each line is one single fish. Do you see something strange in this figure?
It seems like so easy.
Yeah, my gosh. So all the lines that are going down seems to indicate that the fish have become shorter. Doing this like that, of course, it's not. So of course, there are mistakes in this data. So the problem, what is the problem? That when we catch a fish and we release them, we measure the length. Instead, when they are caught by the fisherman, many times the fisherman is measure the length. So there can be some mistakes, some inconsistencies. That's why sometimes you see the negative line. But of course, it's not possible to have a fish that is shrinking during its life, right? But anyway, this data can be used to fit. Remember this growth curve that I showed before, and compare between decades, between years, depending on how many fish we have. So we have done this for different decades, comparing also with the fish that we had in our last 5 years, with our 350 fish. And this was done by Monica then during the PhD. So this is the result. So on the x-axis, you see the years, on the y growth, centimeter per year. of a fish that had the initial size of 40 centimeters. So when we caught this fish, we measured it was 40 centimeters realistic. We were looking how much it was going during this period that it was in the sea. So this is the trend. You see that the growth reached the peak in the 90s, more or less. And a fish of 40 centimeters was growing 10 centimeters a year. So the after was 50 centimeters. Okay. Instead, in the last years, so in 2018 and 19, you see that the fish of 40 centimeters were growing 4 centimeters. So it means that the growth has declined a lot. We don't know anything about mortality doing this, but we know at least that the growth has gone down from the 90s to now. So the fish are not growing somehow. Okay. And these are different growth curves that before. So if we compare this 2016-19, you see that it's much lower respect to the past. So it's a problem, it seems, of growth. The fish are not growing. Okay, doing this experiment also, we tested the otoliths. Remember that I told you before that we were not able anymore to age the fish using the otoliths because we couldn't see these rings on the otoliths. So we want also at the same time try to find another methods of age estimation of the fish, still using the otoliths, but using microchemistry instead. So what we did is that we used also a mark on the otoliths. So the fish were injected by antibiotics that created a percent band on the otoliths. Okay, so when you see these otoliths, it means that this band corresponds to the time in which the fish had been caught and released. Okay? And all this part is the part formed from the release to the recapture. So this was a way to try to give an interpretation of the rings that we could observe on the edge of the otoliths. So if we could learn something about the growth of the otoliths, also not only of the fish. And for this, we had another PhD students that working with this. So what we did was to try to use microchemistry to see if we could age the cod. So instead of looking at this band under the microscope, we try to use these very sophisticated tools. I don't know, maybe somebody's here in the room works with these things. So, for example, this is X-ray fluorescence microscopy. So we had a collaboration with a researcher from Cornell University in USA, Connie Lindbergh, and very nice woman that helped us try to develop a new method to age the cod using microchemistry. And basically the answer that we wanted to ask was if there are some elements, chemical elements that are laid down on the otoliths in a seasonal way. So following the seasonality of the life of the fish. So this is an example not of cod but of flounder. And this is the element, strange y-axis again, but is a ratio between magnesium and calcium. So magnesium and calcium, so what do? You take the otoliths and you scan the otoliths from microchemistry elements. In this case, you take magnesium, calcium, and it seems that the ratio between magnesium and calcium follow something that seems to be seasonal. Okay. So all these peaks and valleys should correspond to 1 year, basically. This needs to be validated. But this was a way to start to use chemistry in order to age the cod. And now actually we know that is possible. So there are some elements that we can follow to age the fish. And one of these elements, very strange maybe to think about, is phosphorus, for example. Phosphorus seems to really to follow the seasonal development of the fish. So this I wanted just to show you how tagging was working. To go in the other slides, in the other file, how can I go? Oh no, maybe it's here. Look. Actually, this I want to go. Okay, if you open the other. Yeah. So this is another presentation because it didn't open. So here you can see the fish that we tagged. So each color corresponds to one country. So Denmark, for example, tagged all these fish in green. Germany, those in yellow. Poland in white. And Sweden in red. So each line actually is a starting point of the fish and the final point. So the first point is where we have caught and released it. The final point is where the fisherman captured it. Okay. Of course, this is a right line. Of course, the fish didn't follow the right line. So who knows what they've done in between. But we know only the starting point and the final point, just to show more or less how many fish we have been tagged and released in different national waters. And remember that there are two cod stocks in the Baltic Sea, separated by these lines. This is the island of Bornholm, that is a Danish island. So you can see that many of these fish actually goes from one area to the other. So there are two stocks mixing in this area. And the mixing, of course, creates a lot of problems. Evaluation of the stock status, management, and so on. So in Sweden, we covered this area. We mainly took fish from gill nets and from trawls, and yeah, just a way to visualize the movements of the fish. Okay. So to go back to the previous, where are they? Here. This. Yes. Okay, so with this tagging project, we were able to see the difference in growth, or the time series in growth in time. We are looking at the movements in space. So there are some analysis that I don't show you about the movement and the seasonal variation of the cod the Baltic Sea. And then also we could see the daily variation of, for example, depth of fish in the Baltic Sea. So for example, this graph is showing the variation in depth while the fish are moving. And you can see there are these peaks following, the daily variation. So usually during the daytime, the individual is more close to the seafloor. During the night, it moves up and is more far away from the seafloor. These tags to follow the vertical migration of the fish, also the temperature that has experienced during this movement. Just to tell you what can be done with this kind of project. Okay, this was it for the project. So in the first part, we have seen what happened to the cod, and mainly the decline in condition and the decline in size. For this second part, we have seen how we could answer the question if it was due to growth, to mortality. About mortality, we couldn't say anything, but about growth, we could say that the growth has declined a lot. From 10 centimeters per year to 4 centimeters per year for a fish that was 40 centimeters long in average. So now in the third part, we want to answer the question why the growth has changed. That is the next step. We try to answer the last question. So we have seen that the growth rate has changed in time, right? So now we want to answer the question why it has changed. If we know that, not. Okay, so I leave the word to you. Why do you think the growth rate of the cod has changed in time? If we focus on the last 30 years, so from the late 80s to now, so the decline in growth rate, what do you think has declined? A bit from what we have seen here today, but also maybe you can think about other reasons, maybe. Okay. Yes. Okay.
That's active fish.
How you say that that fish are in the
No, it's just a salmon cod nowadays to stay in land, but she's colder than Mediterranean.
Okay, so you say increasing temperature, right? Okay. Something else?
Lower oxygen level.
Right.
The same, lower oxygen level.
Lower oxygen. Okay.
And then metabolism and then
Oxygen, something else?
It
Then,
tends to be like a TV.
okay, gauge, there's a process gauge.
The worsening of the conditions. The worsening of the condition factor.
Okay. So the lower condition factor to the factor. We should answer the question why the condition went down.
variability.
Sorry.
Variability.
So we can look, so we are seeing that God is eating the last fish. The fish,
And then species.
but there's from one of the graph, and when the God is small, prefers vertebrates, right? Antipodes, other vertebrates. Okay, so we are seeing gray, temperature, oxygen,
He also
pH.
density dependence, but I would expect the opposite. So density dependence, because normally if density dependence became lower, normally they expect at least that the growth rate of the remaining individuals can go up. But here we can see that the opposite. But that's also less space.
So that's the IMS.
Yeah, that's-
Yeah, so they compact it into more space.
Yeah, so maybe not, yeah, so the density.
Did you hear what was that? Density dependence, so it means that if the density increase, the growth should decline because but do you see this distribution of the size graphic that we said before? So before they were very spread, now they are concentrated. So even if maybe the total abundance decline, all the individual size now are twice. So probably they can. They are in a small space. They are all the same size. Probably they can be smaller than before. It would be. Okay. Let's see.
And so why that increase would be?
We will. We can think about that. Well, this we have seen. If you look at the time scale of condition and of growth, also conditions show increase and then decrease. If we look at hypoxic areas, not so much like hypoxic, also this down. So, but this peak in the 90s is something really something. And if you remember, in the 80s also we have the peak, the population size. That has been the good period for many, and they were growing.
Before the
before the process. But after the collapse, even if there are not so many, everything just down. Fish went down, growth went down, certain maturity went down, parasites went up. We don't know. Nobody said anything about parasites. I've seen the picture before that there was this liver full of parasites, so it can be another reason. So here I just listed lack of food, competition, with physiological stress due to temperature, maybe or oxygen. Also selective fishing, if there is a doorway sharing effect, stuff like that. So we see some of these hypotheses. So in the Baltic Sea, we have a very long-term series of stomach content analysis called. And taken from by many different countries, especially in Poland and in Latvia. Actually, they collected many stomachs of cod during the different decades. So they have data going back from the 50s or 60s. And here you can see the first plot is a growth, is a time series of energy intake. So what the fish could get as energy from what they had in the stomach. So you see that there is an increase also here in energy, and then there is a drop. It seems very nice fitting with the growth curve, for example. And cod is eating mainly this, we said, pelagic fish, herring, but also they seem to like a lot this kind of isopod. It's called Saduria, Saduria entomon. Don't even know if there is in other. I don't think there is. So they like a lot this also invertebrate, because it's quite long, can be up to 8, 9, 10 centimeters. So it's quite big. It's quite easy to catch. Stays on the seafloor. So it's a lot of that. So the energy intake in general is going up and then declined. Okay. Instead, if we look at the proportion between benthic prey and pelagic prey, we see that is mainly the benthic prey who went down. So the y-axis here is showing benthos divided by pelagic. Okay. So this declining is due mainly to a decline in the benthos, in the stomach, in the diet. So both pelagic fish and benthos decline, but declines more than the benthos in the diet, at least. Okay. Somebody said the decline in pelagic prey, and if we look at the distribution of cod, we're seeing that back in time it was evenly distributed in the Baltic, and then starting from the 90s, it started to be contracted in the southwest. If we look at the pelagic prey, actually it shows the opposite. So pelagic prey from the southwest moved to the northeast. We don't know why. Maybe increased temperature, higher production in the north, and so on. So actually now a lot of sprat and herring population actually is not showing here, are in the Gulf of Finland. So up here. So there seems to be a spatial mismatch between cod and the pelagic prey. Could be also due that the cod disappearing from the north have released predation from the sprat, so the sprat population has increased more in the north. We don't know. But currently, there is not so much sprat in the south, where there is a lot of cod. Yeah, so that seems to say that there is not very much pelagic prey there in the south. So there is a spatial mismatch. Another one is hypoxic areas. Somebody of you said that could be a reason of the declining growth or condition. What are the mechanisms to think linking oxygen to growth and condition? It's okay, we can think that, okay, if oxygen goes down, growth goes down, but why? What are the mechanisms behind?
Let's put a maybe
On the seafloor, I mean. So less benthos. Okay, if there is no oxygen, there is no bentos. There is no food for immersed fish. It's called. Okay, less benthic availability than more. Sorry? Physiological stress. No? So they need to spend more energy to survive for basic metabolism. They spend more energy to basic metabolism and they don't eat. Yes. More. Post physiological stress, decline in benthic prey. More what can be. We have said before that many of these individuals became pelagic. So if there is no oxygen on the seafloor, what they do, or they go to coastal areas, or in this case, at least they become pelagic. So it's a demersal species that likes to be on the bottom, eating benthic food, pelagic. And to chase a pelagic fish like a spartan herring, you consume much more energy than just to stay on the seafloor and take what you find on the seafloor, right? It's very difficult to put these values in some equation, but it's possible. Okay, and then we have another problem of the reproduction. We didn't speak about reproduction, but we speak only about growth. But also oxygen is very important for reproduction, at least for the cod. We didn't speak about that, but since there is an oxic area in this region, the eggs of the cod, the eggs are pelagic, so they are in the water column. You know, the salinity is very low in this area. So actually, the egg, what they do, they sink. So they go in the anoxic areas. So if there is a lot of anoxic areas, all these eggs are going to die, all of them. So that's why also the cod has contracted in the south, because the reproduction in the north is zero, basically. So the eggs that are produced sink and die because there is there is something we didn't speak about. So low oxygen affects reproduction, distribution, of course, because all these black or also the gray are areas where the cod cannot be. So they need to move away from that. Benthic prey availability and feeding behavior because they become pelagic. So all these are affecting the cod growth. And actually the new ecosystem of the Baltic now, before there was a lot of cod eating on the seafloor. Now a lot of cod are in the pelagic water because the seafloor is dead in many areas. So they are eating in percent more pelagic, which are much more difficult to catch than benthic organisms. And of course, anoxia is a problem not only the Baltic Sea, but we have experience here from the Adriatic Sea, from the Gulf of Mexico, and from the sea around Japan and the Black Sea, of course. So in the last 10, 15, 20 years, this problem has spread all over the world, not only in the sea, but also in the Great Lakes, for example, in the USA, in Canada, the same problem they have in the lakes. And of course, this is also linked to climate change, increasing temperature, that problem with increasing the oxygenation. So all the mechanisms that relate hypoxic area to low condition and also growth are, one is habitat compression, so the habitat became smaller and smaller. Habitat change, because they become more pelagic. We have direct physiological stress, because living close to area with low oxygen, the fish start to eat less. There are many experimental studies in aquarium showing that when the fish is kept in low oxygen, they eat much less. They don't eat. So the appetite goes down when you don't have oxygen. So they eat less with the physiological stress. And then there is scarcity of benthic food, of course. There's no oxygen, there's no benthic food. So they don't have enough benthic food. All this combined will have an effect on condition and also growth. We don't know exactly what is the strongest effect in the Baltic Sea, but the effect combined can have an effect on the growth. Then there is another mechanism that is selective fishing. It was some colleague of ours that tried to link the declining growth to the selective fishing. So if we have a population with the recruitments or with the small fish that grow in time, so that they become bigger with time. If we go back some years, we had the minimum landing size of 38 centimeters. So it means that if the fisherman caught a fish below 38 centimeters, it was not allowed to take on land. So what he did, or she did, he discarded back to the sea, what we call the discards. Now this is not allowed anymore, but until some years ago, this was still allowed, this discard. So these colleagues were saying that these minimum landing size of 8 centimeters were creating too high density below 38 centimeters. So basically, the density of this fish right below centimeter was increasing, okay, because they were not allowed to be caught. Increasing the density, of course, through density-dependent effect, all these fish were not able to grow, so they became smaller. And the fish, when the fish start to grow slowly during the first phase of its life, then it's very difficult to catch up. So if they start to grow slow, then they continue to go slow, at least in the ocean, then or in the ocean, the sea, if they don't have food. So it means that the declining size, also when they are big, but they are not able to catch up, so they stay small. So according to these colleagues, there was increased competition in small fish because they were not allowed to be caught and landed by the fishermen. Then, of course, we have the seeds and the parasites. We have seen already this picture that many cods have the liver that is basically like this, destroyed, full of parasites. And the liver is very important for the cod. So the cod accumulates energy in the liver. But there are many fish accumulating the fat where in the muscles or around the stomachs, intestines, but the cod accumulates energy in the liver. So when the liver looks like that, it's very difficult for the cod to use the energy accumulated in the liver. And the problem with the seals is that the population of the seals has increased a lot in the last 20-25 years. And the seals is the final host of this parasite. So it seems that the more seals you have in the sea, the more there is the risk that the cod gets infected by the parasites. So now in Finland, in Sweden, Denmark, probably, we are talking about shooting seals. So they decrease the abundance of the seal population. But really, it's not a joke. So of course, this creates a lot of conflicts between conservation groups, fisheries groups, and so on. But this seems to be, another way to try to solve at least this problem. Yeah, this is now the photo showing the life cycle of these parasites. So they see the final host. The parasite lays eggs. They go through the whole food chain. They go first in the plankton, in the invertebrates, then the plankton is eaten by pelagic fish. Pelagic fish are eaten by cod, and then seals eat cod. Okay, so the seals is the final host. Okay, so we have seen the declining growth of cod. We have seen that the decline or the decline in the size structure of the cod. We have seen that this has been due at least partially to the declining growth. We have seen different theories about why the growth has declined. And so one question that we can ask ourselves now, if it's possible to get back the cod as it was in the 80s, 90s, at least in size. In populations, I have my doubts, but in size, so in body size. As you have seen before, I mean, the peak in the cod population was in the 80s, 90s. No? There was this big peak when it went down. So this peak in the 80s, 90s was something never seen before. If you look in the last 150 years, this peak never seen before. So something happened very that was able to increase the recruitment of the population, increase the growth, the condition, and so on. But now the question is if this is possible to go back to the situation of the 80s, 90s, the population size, but also in the body size. So that is a question that we want to know, because what we want to do is try to do some kind of management action, trying to help the cod in abundance and in size. As I told you before, I'm a bit skeptical about that, because for me, there is no room for cod in the Baltic Sea in the future. The salinity is going down, temperature going up, oxygen will not be solved. So you can ask yourself the question, why we need to care about cod? That we care about other species. And in Sweden, at least, they've been talking also about trying to oxygenate the water again. Back in time, there was any project thinking really to oxygenate the water again with big pipes. So from land to the deep areas. And there was a university, Gothenburg University, for example, trying to solve the technical problem, how to do this. So one solution was that, to oxygenate the deeper water of the body by some pipes. But then in the last years, I never heard talking about that anymore. I don't know what happened with that project. Okay, recovery. What time is it? See if we make it. You are tired? A bit? So let's see how to summarize. Here we go in scientific ecological theories. You know the theories about the alternative stable states. Who did ecology maybe knows. So if we focus on this graph, this you see on the x-axis the condition, external condition like salinity, temperature, oxygen, fishing pressure, whatever. On the y-axis you have ecosystem state, can be whatever, can be population size, can be growth rate, can be whatever. So according to this theory of alternative stable states, this theory says that when the ecosystem shifts from one state to the other, it's basically very difficult to go back to the original state. Because why is impossible or very difficult? Because in the new state you have something keeping very resilient, very stable, the new state, because of new feedback, positive feedback, keeping the state in the new ecosystem in the new state. Okay, so when we ask this question, if the Baltic ecosystem or the Baltic population can go back to the previous state, we need to ask if there are positive feedbacks keeping the state in the new, keeping the ecosystem in the new state. You understand? Okay. So let's try to look at this. So this, I just skip it. Everybody understand the positive feedback concept, right? So there are new mechanisms, biological mechanisms, keeping the ecosystem in the new state. In our case, the state, what is the state? The state of low population size of the cod and low growth. Okay? With something keeping this biological condition stable, resilient in this case. Okay? So in this case, resilience is not a positive thing. This characteristic. This is a typical example that the books do try to explain positive feedback, relative stable states. We don't go there. You understand the relation between vegetation and rain. If you have more rain, you have more vegetation, right? If you have more and if you have even more, even more, so that is a positive feedback. To go away from that because it's auto-reinforcing. So let's see if we see some kind of this mechanism in the Baltic Sea, for example. So we come back this. Okay. So if you go back to the Baltic Sea, this is also a study of my colleague. So you have the time series of code, population size, so biomass, abundance, numbers, and then also sprat. Here stops 2010, but you can imagine that the code stayed very low, the sprat stayed high. And the other plot, you see that on the y-axis you have the cod biomass, and on the x-axis you have the fishing mortality. So how much fish dies because of the fishing. Okay. And you can see that at the same level of fishing mortality, you can have totally different levels of cod biomass. Okay. So at the fishing mortality of 0.5, whatever it means, you can have 200 kilos of cod, but also 1,000 kilos of cod. Okay. Even if the fishing is very important for the difference for the change in cod biomass. So now we want to understand why actually the cod population continues to be low, even if the fishing has been totally closed in the last 3 or 4 years. Fishermen are not allowed anymore to fish in the Baltic Sea for cod. There are some recreational fishing, some gillness fishing, but trawling is totally forbidden now since 3 years back. But the cod didn't show any even small sign of recovery. Okay, you can see it's only 3 years, so cod needs time, of course, to recover. But what are the mechanisms that can keep cod in a low abundance state? Can you think about some mechanisms? So the cod population goes down due, for example, to temperature, salinity, fishing mortality. Why now it's very much difficult, more difficult for the population to go back to original. So
they have the less resources.
Okay, that's true. So the sprat is pelagic fish, also herring. It is more or less of the same size. An herring can be in the 40-20 centimeter. It can compete for a cod of 10, 15, 20 centimeters. Also small cod are pelagic. So they eat the same thing. So if the population of cod declines and the population of the pelagic fish increase, the pelagic fish can outcompete more cod for the resources. You remember this graph that pelagic fish feeding on the plankton caused the decline of the plankton. So if there are a lot of pelagic fish, and there are a lot of pelagic fish because there is no cod anymore, these are eating plankton that also cod larvae are eating. So there is a competition for plankton, for example. So that can be one mechanism. Another one, so competition. You read the literature on the Baltic Sea? No, you didn't. Exactly.
Example, anchovy and
Yeah.
many of these things.
Yes. So sprat and herring, the pelagic fish, eat cod eggs. A lot of cod eggs. This is another mechanism. The third is a bit more difficult. It's through
For FTX.
yes, yeah, FTX and also amount of eggs. This is what they're showing you. This is comes from the ecological theory. So the first feedback, remember this positive feedback, is that the prey compete with predator for early life stages. So pelagic fish compete with cod for plankton. The second one is the one called cultivation differentiation. That doesn't mean that the prey feed on cod eggs. The third one is the one acting through fecundity. What does it mean? That when you have a lot, not so many predators, the prey increase in abundance, but then what they do also? They decrease in size because there is competition in the prey. They decrease in size. They are thinner. They are shorter, so they produce less eggs, and they produce less young. And the cod likes to eat small pelagic fish. Okay, so there is lower recruitment of pelagic fish, so not enough food for small cod. So it creates a bottleneck in the early life stage of the growth of cod. These are all things that are explained by ecological theory. Then we are not sure that these apply for the Baltic Sea, but we know from the data that, for example, the fish eat cod eggs. We know that they compete for plankton. We know the fecundity of pelagic fish are decreasing. So we know that this happens, but we don't know how strong these mechanisms are on cod, of course. Okay, so this is it creates different feedback loops, keeping the new state stable. So when we have a lot of pelagic fish eat on the plankton, so there is not enough for cod larvae. Pelagic fish eat cod egg. And also the third mechanism, the third feedback loop through fecundity. So when we have the disappearance of the big predator, the trophic cascade, the increase in the pelagic fish, there are these new feedback loops keeping the cod population low. Even if we should stop fishing, like a norm. These are in theory, then we don't know if these feedback loops are so strong to be the cause of the lack of recovery of the cod. So then there is another feedback. Then we stop with feedbacks. So we have seen the feedback through trophic cascade. So if the cod disappears, there is more pelagic fish. Okay. If there are more pelagic fish, there is less plankton, but more phytoplankton. If there is more phytoplankton, this increases the problem of anoxia. Yeah, everybody understands why anoxia is worse if there is a lot of phytoplankton. So this phytoplankton, before let it die, sink, and then the bacteria consume oxygen to decompose the phytoplankton. So the anoxia problem increases even more. And if there is anoxia on the seafloor for cod, not so good, no? So there is another feedback loop. And then there is the last feedback loop to the nutrients. Because phytoplankton, increasing the power of anoxia, increase the suspension of the nutrients, or the phosphorus maybe. Because the phosphorus in the Baltic Sea, when it's produced, it sinks in the sediment and stays there. If there are anoxic conditions, this phosphorus is suspended in the Baltic Sea, in the water. And if there is more phosphorus, there is no more nutrients for phytoplankton. So there is another feedback. So the disappearance of cod can create a lot of new positive feedback, keeping the cod population down. So you need to break these feedbacks in order to have again the population. Okay, and then of course we have the seeds. The seeds we already forget, but in the end there are also the seeds. That has nothing to do with cod probably, because the seeds have increased again after decades of hunting in the past, in the last century. And hunting was very limited, so that's why the seal population started to go up. But now the governments want to start to kill again the seals because they think that this will help the cod. Okay. And this, we talked also about this. So parasite can have an effect on growth, but also mortality, direct mortality in cod, because when cod has such a liver, it will die. There is no room for surviving. Okay, so actually it's very difficult now for cod to go back to the same population size as before. So one, before the ecosystem has changed, like temperatures increased, oxygen has declined, seals have increased, but also because of this positive feedback, ecosystem feedback keeping the cod population low. So the last question that we can answer is that, okay, so if we want to save the population, what can we do? So that we go to the management part. First of all, do we want to get back the cod? That's the first question. Why we want to go back the cod? Exactly. Cultural factors. Back in time, it was much more arid. The food, for example, for Swedish, for Finnish, for Polish was arid. Then cod started to increase in size in the 80s, 90s. So the cod started to be the best food for dinner for many countries. But it's not sustainable. The fishery for cod is not sustainable. You spend more money fishing cod than what you gain selling the cod, actually. So first of all, we want to get back the cod. It's not better to eat something else. But if we want to get back the cod, what can we do? Your colleague saying fishing on sprat. Because if we believe in this feedback loop, we're saying if we decrease the size, there will be more plankton food for cod larvae. There is less predation of cod eggs, and there is less phytoplankton bloom if we believe in these trophic cascades. So we release of this feedback loop will be weaker, and this maybe will make a recovery of the cod population. But we expect the cod population to get back to the level of the 80s, 90s. I think it's impossible. Possible because salinity is continuing to go down. Sorry? Yes. Temperature is continuing to increase, salinity is declining because it's raining more. So creating this already low salinity of the Baltic Sea even lower. And we have seen that if salinity is low, the eggs sink to the anoxic areas, and there is no recruitment for cod. So why we want to save the cod? That is the question. That is a political decision based not only on science, but on society, cultural factors, and other things. But if we want to get back the cod, so one is to fish more sprat. Why not? And this actually was discussed at the Commission level, EU Parliament, and so on. You remember that there was this threshold in. Now I go quick because you remember this threshold. So the sprat has an effect on the plankton only when sprat abundance is above this threshold. So one thing that we discussed in European Commission, EU Parliament, stuff like that was if we should use what is called the escapement biomass. So saying that we want to keep the biomass of the sprat population below the threshold.
Reference point used in the.
Yeah, we want to fish more. Yeah, exactly. What's part? And why we want to fish more? Because having the sprat abundance below the threshold doesn't have effect on the plankton. And also because by keeping low the sprat population, the sprat individuals will grow much bigger, much fatter, and will produce more eggs. Food for cod, or small pelagic fish food for cod. Yeah. Because this was discussed a lot more or less 10 years ago. Then We never reached to a conclusion to that. It was too risky probably to do that. Because of course to try to do something new, you need very strong base to make, I don't know, the politicians at European level really to do this, really to prove that it's true. Of course, it was very difficult to do that. But that would be one ecological option to do that. Other options that you see?
Wait for the effect of the explosion.
Sorry?
Waiting for your opportunity to the closure to have an effect.
So the fishery is closed, but you say that wait, then probably it will be an effect. And yes, this can be an option. That's why actually the fishery has been closed to try to help. But in these 4 years, we didn't observe any increase in recruitment and increase the biomass and increase in growth. Now, of course, it takes time because the cod reproduce. I don't know now at what age, but we know that the size is 20, 25 centimeters. It can be 3 years of age. So maybe we need to wait a bit more to have an effect on the population. But the closure of the fishery also happened in the, of Canadian cod. Canada, they did the same. The cod collapsed, they closed the fishery, more or less closed. But
It's a lot.
25, 30 years, yeah, so but never came back, the Canadian cod. And also there, they are saying that the ecosystem has changed so much, so now the ecosystem is dominated by the cod preys that are keeping also their cod population. By feeding, by competition, by predation and so on. So even if in the case that we had the closure of the fisheries, many times we didn't get back the population. Okay, this could be a management. The first one, what was that? Okay. Yeah. So the first option would be to keep low the population size. The second option would be to fish more on sprat or less sprat in the south, where there is a lot of cod, so there is more food for cod. That is contradictory with the first option. Other options that you say?
And you can release the eggs.
You can?
Release the eggs of putting like billions of eggs that's not good bad.
Then if you are trying.
This stage,
Yeah.
units.
There is something going on. I mean, in Denmark, they are doing. They are growing fish and spawn eggs in tanks, and then release these eggs and larvae. Let's see. That is something going on. You can ask to your colleagues in Denmark what they are doing. So that is another one. Yes. Something else. Let's see. Another thing that we didn't discuss is about the relation between cod and another species that is flounder. There's a lot of flounder. Flounder is a flatfish competing with cod for food. For this, you remember these isopods, Saduria. So another thing that now we are discussing is instead to fish more flounder. More flounder because it is a good fish. I mean, from a cultural perspective, nobody wants to eat flounder. I mean, in Sweden, nobody wants to eat flounder. But in the Baltic states, like in Latvia, Lithuania, Poland, this is very delicious fish and it's good. But there are cultural reasons why in Denmark and in Sweden they don't want to eat flounder. But one other option would be to eat more flounder, so eat flounder instead of cod. So fishing more flounder and then could release predation, competition with cod. So could help also cod to recover. So these are all options that are based on ecological consideration that are very difficult to apply because the managers, of course, before applying some change in management decisions, want to be sure about what they do. But this could be another option. The last option, and then I leave you, is remember this figure about minimum landing size or conservation size. These colleagues are saying that actually these 38 centimeters, 35 centimeters now should be decreased. So that should be brought lower, so like 30, 25, 20 centimeters. So to release these bottlenecks of competition for small products. They start to grow already faster at the early life stage of their life. So these are all the different options that have been discussed in the past. They are still discussed now. And between flounder and cod is quite difficult to. You can play with the mesh size because, of course, flounder is a flat fish, so they are totally different shapes of the body. So you can probably do something with the mesh size. But about area, they quite live in the same habitat. So if you want to catch flounder and also cod, you need to work with the mesh size, with the gear, because they live in the same habitat. Okay, so we have just to finish. We have talked about the Baltic Sea. We focused on the cod, spot, and herring, but we know that there are also seals. We have talked a bit about seals. We have flounder. We have pelagic birds that are catching a lot of pelagic fish, and we have this new small fish that called three-spine sticklebacks that has invaded now the Baltic Sea. Has increased in abundance enormously in the Baltic Sea, and we need still to understand the ecological effect of these small fish in the pelagic food web. Now the fishermen want to start to fish also on these sticklebacks. It's very small fish, 3, 4, 5 centimeter maximum. He has spines, and it cannot be used to as human consumption because it's too small. And but the fishermen want to fish to produce oil, fish meal, flour, and this was a species that was fished a lot back in time, where they made oil from this fish. So now the fishermen want to start to fish on this, but before getting permission to do that, they need to. The politician wants to know the effect of the fishing on the ecosystem before allowing all this. Okay, but I just summarize. This is the last slide. So the Baltic is a very sensitive sea. It's closed, it's brackish, so low salinity, has very low biodiversity. There are many pressure acting on the Baltic Sea, like in the Mediterranean. There are 9 countries bordering the Baltic, 8 European countries and 1 Russia. So the political situation is not easy. The cod is in a situation of distress. So we have seen all these biological changes. Now the population is constituted by thin and short fish with big ecosystem and economic effects on the fishery. The reason of this decline in growth not known yet, so we need to study a lot more on growth and mortality of the species. So there is room for scientific studies still, even if the Baltic Sea is the most studied system in the world, but we need still to have basic biological, ecological knowledge. And then it's important to include the ecosystem consideration into management, even if it's not easy. And the last thing that I repeat a couple of times is that the cod is always at the center of the scientific debate. If you look, take a newspaper, you see cod. But for me, I mean, it's better to focus on other species actually than on cod, because I don't see any very light for these species in that area. We finish here. If you have questions, we take times.
The hypoxia condition wasn't it protected the same way?
It seems to be more tolerant flounder than cod, much more tolerant. So we can find flounder also in area where there is not because of low oxygen. But they can survive good also at low level of oxygen. So and cod and flounder you can find also in the northern Baltic Sea. If you go close to the Gulf of Finland, in close to Estonia, Latvia, there's a lot of flounder. White cod totally disappear from those areas. It's much more tolerant to lower salinity and lower oxygen concentration. It's a strong fish. Also.
So did you see an increase in the with the decrease of salinity of the basin?
As I said, the population of sticklebacks just increased exponentially. That was coincident with the decline in salinity in the surface water at least. So could be due to that, but we don't know yet what. Also, the temperatures have increased, the carbon production has increased, and these are all conditions that seems to be good for sticklebacks.
Option even to consider the set the change of the ecosystem. You know, that this new low condition of God. What I understood, your opinion, probably likely to recover from this condition, no? Then I mean, even or in other countries, there in this kind of thinking about to accept that is living, because in general there is a stronger issue than every want to or yes politics, for example.
I mean, much that is done currently is done to try to protect the cod. See, so shooting the seals and the other discussion that I presented here are for saving the cod.
And
So we are still there. We are still there. We want to preserve the cod to continue to eat cod in the future, even if now the fishery is closed, so we're not eating Baltic cod anymore. Still, I mean, there is pressure, maybe also from the customers too. Customers and for the public to have cod in the sea. And I think maybe I'm strong, but it's a waste of time right now to do that. I will focus on other things.
A good chance to teach people even to eat other species to diversify.
Enough, for example.
The environment of number of species. I mean, this should be fundamental to each all of them, at least.
But in both, we are going in that basis. This is another fish coming from the Caspian Sea and the Black Sea that has been introduced to this ballast water. Ships coming from the Black Sea and Caspian Sea, Baltic Sea, bringing in invasive species. Now in the coastal areas, the increase of this, which are very fat fish and tasty fish. So some countries are starting to eat and you can ask. Okay, there are invasive species. You can also probably think, okay, it's good to have them here. So we should sell those species now or not. Push them back again. But I think you need to be adapted to it. If you have with just like 10 of the and you've seen the cotton for the cotton. They are destroyed. They are feeding, they're full of parasites. So the cod that also very in the area of Scandinavia, coming from the Black Sea. Why would we? work with that actually. So it's easier, cheaper to buy food from the variety. It's now this economic no sense. Yeah, and then the water area is flat, right? They are fat fish usually, but in the water they are very thin. So small. Because the fat is not eaten. We don't massage. So they utilize again oil, flour, tissue. Dairy instead can grow very big, so they can use massage. Tasty taste, maybe and like that taste this much. I recall to play on some specialties which have this one. Fish food and but I think like the body is very thin, also it's not fashion. Flour, oil.
Because Northern Sea is a quite good food, delicious food.
Yeah.
I mean,
Yes, but don't take it with them, for example, on the other side, because in the North Sea, this part is very fat, very useful for you, but not too much. Okay, so this was a very quick summary about what fish, ecology, trophic interaction, people management, and I hope it helped for what. Yeah. So good luck for your PhD. See you